Hello everyone, and welcome back to our virtual chemistry laboratory. This week we're talking about titration. The title of the experiment is volumetric analysis, which basically means determined by volume. Titrations are very important in chemistry. They cover a wide variety of approaches and techniques, but the goal is generally the same, and that is to figure out exact concentration of a solution, which is typically added from the burette to another solution in the flask. The solution added from the burette is called titrant. And in our experiment today, we're using sodium hydroxide solution whose concentration is approximately 0.1 molar to find its exact concentration. The sodium hydroxide solution is going to be in the burette, so it's going to be our titrant. And we're going to titrate sodium hydroxide against a substance called potassium hydrogen phthalate. Here is the name. It's abbreviated as KHP. So when you watch other videos that I posted on Canvas, it will talk about KHP. It does not mean a chemical formula, rather it's an abbreviation of a name. The chemical formula of KHP is shown right here. This is an interesting substance because technically it's a salt. It as follows from its name, phthalate. Ending A typically means it's a salt, but it's not just your regular run-of-the-mill salt. The salt has this hydrogen ion here, which makes it also acidic. This hydrogen can dissociate in water, producing a H+ ion, and therefore the substance can also be considered an acid. We're using potassium hydrogen phthalate here as a primary acid, meaning it's a solid. It's not very common for an acid to be a solid. Most acids are liquids. And so using this substance as a solid allows us to exactly find the amount of it by weighing an exact mass of it for titration. So as I mentioned earlier, the goal of the experiment is to determine the exact concentration of approximately 0.1 molar NaOH by titrating it against the primary acid, which is KHP. The reaction here that we are considering can be defined as neutralization reaction. We talked about these reactions briefly in the beginning of the semester. We mentioned that neutralization reactions occur between an acid and a base, and typically involve formation of a salt and water. So here is our acid, potassium hydrogen phthalate, reacting with a base, sodium hydroxide, producing in this case a mixed salt of potassium sodium phthalate and water. The chemical equation of the reaction is important because it shows us the molar ratio of the reactants. You can see that 1 mole of KHP is expected to react with 1 mole of NaOH. This assumption here is the key to the rest of our experiment. The idea is to start with certain known amount of KHP, certain number of grams of KHP. It's a solid, pure substance, so we can find, if we know grams, we can find its moles. Molar mass of the substance should be provided in your lab manual. And then the goal is to establish in a titration a situation where we stop adding base to KHP in the flask when number of moles of NaOH and number of moles of KHP are equal. And then if we know moles of KHP, we can find moles of NaOH. As you can see, it's going to be 1-to-1 ratio, so moles of NaOH will be equal to moles of KHP. And then if we know moles of NaOH and we know volume of sodium hydroxide solution that it took for us to get the reaction to come to completion, we can find molarity or molar concentration of NaOH. So what you're going to do in your report sheet is you're going to start by finding how many grams of KHP would be theoretically needed for titration. You're going to make a couple of assumptions here. First assumption is that volume of an AOH needed will be 20 milliliters, as you can see right up there, can't quite reach. So volume of an AOH here will be equal to 20 milliliters, and you're going to assume that molarity of an AOH is roughly 0.1 molar. It's right here also, right up there. So using the volume of an AOH and its molar concentration, you will calculate moles of an AOH, and then you're going to assume that moles of an AOH are going to be equal to moles of KHP, because again, it's 1-to-1 ratio in the balanced equation. And then once you know moles of KHP, you can find grams of KHP. So what are these grams of KHP? These are grams of KHP you theoretically would weigh and use for your titration. Then you're going to assume that that mass of KHP was titrated against sodium hydroxide until a so-called equivalence point is reached. We need to talk a little bit more about what it means, equivalence point. Equivalence point means is that all KHP in the flask that we started with is just neutralized by sodium hydroxide, but no excess of an AOH is added. So you basically add an AOH from the burette until the last little bit of KHP remains. And as soon as all of the KHP has reacted, you stop adding an AOH. And at that point, you can then assume again that moles of an AOH are equal to moles of KHP. So what will be provided to you in the email from your TA will be the mass of KHP that was actually used for titration, which should be close to your theoretical calculated KHP mass. And then we will also provide you with volume of an AOH, and you will have to find exact molarity of sodium hydroxide. I would like to show you several things here real quick. I'd like to point out that I did post several videos on Canvas that talk about use of the burette, preparation of the burette for use, and also guides you step by step through the actual procedure. So I'm not going to show you the procedure, I'm just going to make some important points. So what I'm holding in my hand is called a burette. Burette is a special type of container used in chemistry, device you could say, that is used to measure exact volume of a solution. Burette consists of what's called a barrel, this glass portion here. It has graduations on it, and then on the bottom there is a glass tip, and in the middle between the barrel and the tip there is what's called a stopcock. It's made of Teflon. Stopcock can be operated to allow liquid to either come out in full stream or in drops, or not come out at all. Right now I have my burette stopcock closed, so no liquid would come out, but burette right now is empty. So what I'd like to show you next is how to wash the burette. So I'm going to walk over here with my stopcock closed. I'm going to pour a little bit of deionized water into my burette, about a little bit more, roughly a third. And then I'm going to hold the burette almost horizontally, and I'm going to rotate it so the liquid inside, in this case water, washes the entire inner surface of the burette, like so. And then I can pour out the water like this. Typically burette is washed at least 2 or 3 times with deionized water, and then a couple more times with a solution that will eventually be used in the burette. In our case it's sodium hydroxide. I'm not going to show you washing with sodium hydroxide simply to save time. Instead, I'd like to show you how you would fill the burette and how you would read it. So what I have here is a ring stand and a special burette holder. The burette can be slipped in between the side arms of this holder, and this allows the burette to stand upright. So I'd like to talk about graduations a little bit. I'm going to move this closer so you can see. I'm going to hold a piece of white paper behind the barrel so you can clearly see how burette is graduated. You can see that burette is graduated from 0 on top down to 50 on the bottom. So this is a 50 milliliter burette. The burette has graduations of milliliters. You can see the numbers. So 50 is down here, and 0 is up here, and then goes 1, 2, 3, and so on. So these are milliliters, and as you can hopefully see, there are 10 graduations in between each milliliter mark. So the distance between two nearest graduation marks would be 0.1 milliliter. We typically read the burette to the nearest 0.05 milliliters, which is half of this tiny distance between graduation marks. So what I'm going to do is I'm going to put my goggles on here, and then I'm going to put, I'm going to lower the burette since I'm short, so I need to lower it so I can reach. I'm going to place a funnel on top of the burette, and then I'm going to pour the liquid into it. So typically what you would do is you would fill the burette to above 0 initially. You can see my liquid is well above 0. And then before you begin titration, if this was, say, sodium hydroxide, you would have to first make sure your tip of your burette is filled with liquid. So what I'm going to do is I'm going to open the stopcock and allow the liquid to fill the tip. I'm still above 0 right here, so I'd like to get my initial reading before I start my titration. So what I'd like to do is have my initial reading somewhere between 0 and 1. It is not necessary to have it right at 0, because you can always take initial reading, record it, and then later subtract it from your final. When you're reading the burette, it's important to make sure your eyes are aligned with the level you're reading. So I'm going to drain a little bit of liquid, then I'm going to lower the burette, and then I'm going to take my reading. So my bottom of the meniscus, which I have to read, is now a little bit below 0. I'm going to lower this so I can see better. And I'm going to put my white piece of paper behind it so we can take a look together. So it seems to me that the meniscus is right between 0 and 0.1. So this would mean that I would record my initial reading here as 0.05 milliliters. So any volume in this experiment that would be read from the burette would have to have 2 digits after the decimal, second digit being either 0 if meniscus happens to be right on the line, or 5 if meniscus happens to be in between 2 lines. Now we're going to talk about the use of the indicator in this experiment. The indicator used in this experiment is called phenolphthalein. It's an organic substance that here is used as a solution in alcohol, and we typically add about 2 to 3 drops of this indicator to any of the solutions. So I have several flasks here that I wanted to show you. So here I have some acid. It's actually hydrochloric acid and water. And I'm going to add some phenolphthalein. We're going to see what happens. And as you can see, there's pretty much nothing happening. Solution is still remaining clear and colorless. So bottom line is phenolphthalein is colorless in acid and the neutral medium. And here I have some sodium hydroxide that I added to water, and I'm going to add some phenolphthalein. I'd like you to see what happens. So this is base and some phenolphthalein in here. Oops, I'm making whole thing. Activating base. So this right here is approximately 0.5 molar sodium hydroxide. I'm going to add a couple of drops of that, and now I'm going to add some phenolphthalein. So as you can see, the solution turns very dark pink color. This is the color of the solution containing base and phenolphthalein. So phenolphthalein turns pink in base. So when you would be doing your titration and you would add phenolphthalein to potassium hydrogen phthalate, which remember is an acid, you would not have any color change, so it would look pretty much like this. And then you would begin adding sodium hydroxide slowly from your burette until you got equivalence point. The thing to point out that at equivalence point, the solution should be barely pink. I hope you can see. I might hold it like this so you can actually see. The color you want for equivalence point is very, very light pink. This indicates that all of the KHP has been used up and pretty much no excess of base is present. Maybe just a tiny little excess of base, which helps us get the color. Ideally, of course, moles of acid and moles of base would be equal. So this is the color you would have to titrate to. Major challenge with the titration is to have enough patience to basically add base slowly enough so that instead of something like this, you would get something like this. So that would be the goal. So once again, you can expect to get an email from your TA where data for the titration will be provided. You will be given mass of KHP used for titration, and you will be given volume of sodium hydroxide used to get to equivalence point. And then you will have to calculate moles of KHP, and based on that, moles and molarity, exact molarity of sodium hydroxide. I'd like to add that molarity of sodium hydroxide that you calculate must have 4 digits after the decimal. This usually means that solution of base would be considered standard, meaning its concentration is known exactly. All right, everybody, till next time.